Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Hello students, good morning. Let's now study about some important compounds of silicon. Earlier in the previous chapter, we have studied about allotropes of carbon and also some important compounds of carbon, particularly carbon monoxide and carbon dioxide, and also uses of the carbon containing compounds or carbons. The silicon dioxide, some important compounds of silicons are mostly that is there in our syllabus is silica or the silicon dioxide, silicon, zeolites, and so on. Let's first start with silicon dioxide, the SiO2. This is the empirical formula of silicon dioxide, SiO2. The 95% of the Earth's crust is made up of silica and silicates. One thing you should remember, this is not the molecular formula because silicon dioxide or silica doesn't exist as it doesn't have the discrete molecules. So whatever the crystal that you take, you can consider the entire crystal as a single molecule. So, but one can obtain the empirical formula as this. And the similar thing that the diamond as well. Whatever the amount of the crystal that you see, the entire crystal can be considered as a molecule. There is no discrete molecule formation in such these compounds that we see, like in the diamond and silica. 95% of the Earth's crust is made up of silica and silicates. Silicon dioxide, SiO2, commonly known as silica, occurs in several crystallographic forms. So it occurs in several crystallographic forms. Some examples are quartz, cryptobelite, tridamite, are some different crystallographic forms of silica, which are and these are interconvertible. These crystalline forms of silica are interconvertible at suitable temperature, so they change from one form to different forms depending on the temperature. So silica exists in different crystallographic forms. Some examples are quartz, cryptobelite, tridamite. And the silicon dioxide is covalent three-dimensional network solid in which each silicon atom is covalently bonded in a tetrahedral manner to four oxygen atoms. If you look at the structure of the silicon dioxide, SiO2, what you see, each silicon is attached to four oxygen atoms. But however, what we have, it is shown in the two-dimensional planar structure. You don't see formation of the planar structure. Each silicon atom is tetrahedrally attached to four oxygen atoms. So we see 109-degree angle and not 190-degree angle as we see on this plane. So the oxygen atoms are tetrahedrally arranged around silicon atoms and there are four bonds. So silicon is here sp3 hybridized. Each silicon atom is sp3 hybridized. Oxygen is also sp3 hybridized. And so the distance in the sp3 hybridization, oxygen also contains two lone pairs, and so with the lone pairs and two bond pairs, oxygen also takes a tetrahedral structure or tetrahedral shape. With if you consider the lone pairs, and the silicon anyway four bonds are there, and they are all the atoms of silicon are involved in the bonding. The four bonds are there, four bond pairs. These bond pairs are arranged in the tetrahedral geometry. And the similar thing that if the silicon geometry is similar to the carbon geometry in the diamond. So if you just consider here this carbon atom, so this carbon atom is tetrahedrally attached to four carbon atoms in the silicon dioxide. If this one is silicon, so these atoms will be the oxygen atom. So this is the only difference that we see there. So each oxygen atom in turn covalently linked to two silicon atoms. So in turn, what we see, oxygen atom is associated to two silicon atoms. This is because oxygen has only two covalences. Covalence is only two and silicon's covalence is four. So silicon can form four bonds and oxygen cannot form more than two bonds because oxygen's octet is complete in this case. If it forms third bond, there will be positive charge on the oxygen. So each corner is shared with another tetrahedron. So what we see, each corner, if you consider this corner or this corner will be shared with another tetrahedron. Another tetrahedron is another SiO4 unit. And so this is how we form the three-dimensional structure of the silica. The entire crystal may be considered as a giant molecule. As I said, whatever the crystal size, one can consider that entire crystal as a giant molecule. And a similar thing one can do for the diamond as well, in which eight-membered rings are formed with alternate silicon and oxygen bonds. So what you see, one can see the formation of the eight-membered ring. This is the eight-membered ring, you, in which four silicon atoms and four oxygen atoms are involved in forming this ring. So this is eight-membered ring where silicon and oxygen atoms are alternatively arranged. Silicon forming four covalent bonds with the four oxygen atoms, and oxygen can form maximum two covalent bonds with two silicon atoms. So again, I'll repeat this. The entire crystal may be considered as a giant molecule in which eight-membered rings are formed with alternate silicon and oxygen atoms. Silica in its normal form is almost non-reactive, and why it is non-reactive? Because silicon oxygen bonds are strength is very high, and so its bond dissociation energy is also very high. So one can call the bond very high silicon oxygen bond enthalpy, or the bond dissociation energy. So the bond dissociation energy. The bond enthalpy of silicon oxygen bond is very high, and that is why silica in its normal form is almost non-reactive, and that is why we see the entire earth most of the portions of the earth crust is made up of the silica, and it resists the attack of by halogen. Since this SiO bond enthalpy is very high, so silica resists the attack by halogens, so it doesn't react very easily with the halogens or the dihydrogen and most of the acids and metals even at elevated temperature. So even at higher temperature, it doesn't react. Silica doesn't react with most of the acids and the metals as well as halogens and dihydrogen. However, silica may react with HF and NaOH. And why this SiO bond is very strong? Because silicon has very high affinity with oxygen. Another reason for high affinity for silicon with high affinity with oxygen could be the oxygen has a lone pair and silicon has a vacant d orbital, so the one can consider a partial double bond character as well. So that this kind of thing actually leads to very high SiO bond enthalpy. Although you see there is a mismatch in the size of silicon and oxygen. There is no mismatch in size of carbon-carbon bond in diamond, but here in the silicon and oxygen we see the mismatch in size. But because of this oxygen affinity of silicon with the oxygen is very high, and that higher affinity is because of the presence of vacant d orbitals in silicon, and the mismatch in the size of the orbitals is also not very high. It's a slight mismatch is there, but that mismatch is not very high, very exaggerated. So it resists the attack. That is why the SiO bond enthalpy is high, and so it resists the attack by halogens, hydrogen, and most of the acid. However, what we see, silicon can have has even higher affinity with the fluorine, because fluorine has similar tendency with oxygen. So silica can be attacked by HF, though it forms and it forms SiF4. Although it doesn't form SiF4 when the F2 molecule attached to the silicon. But if the acid is there and the acid, because of the acid H plus formation, oxygen is a lone pair. So this kind of reactions that we see, the hydrofluoric acid can react with the silica to form SiF4 plus 2H2. However, HCl, silica doesn't react with HCl so easily. So the SiO2 plus 4HS we get the formation of SiF4 plus 2H2O. Silica similarly react with NaOH and it forms sodium silicate plus water molecule here. Some usage of the silica are quartz, one of the crystalline form of silica, is extensively used in piezoelectric material. And the piezoelectric materials means what? There are certain materials which have ability to generate internal electrical charge when a mechanical stress is applied on the material. So you just provide a mechanical stress on the material, and you will see some internal electric charge generate in that material. Such materials are called piezoelectric material, and the piezoelectric material, this definition comes from the piezoelectric effect, which is the induction of an electric charge in response to an applied mechanical strain. To apply a mechanical strain and you see the induction of electrical charge, such behavior is called piezoelectric effect. And so the quartz is extensively used as piezoelectric material, so it shows piezoelectric effect, and it has made possible to develop extremely accurate clocks, modern radios and televisions, broadcasting and mobile radio communications. Silica jelly is used as a drying agent and as a support for chromatographic materials and catalysts. Kieselguhr, an amorphous form of silica, is used in filtration plants. So this is amorphous form of silica which is used in filtration plants for the filtration purposes. And silica, what we see, silica gel is also the drying agent and support chromatographic material and catalyst. So it also acts as catalyst. The next compound of the silica is the silicones. This is a polymer. Silicones are polymers. So silicones are a group of organosilicon polymers. Organosilicon polymers means the carbon and silicon bonds will be there, and so this is such compounds are called organosilicons or organic compounds. Carbon containing compounds are called organic compounds, and if silicon carbon bond is there, you can call such compounds organosilicons. And silicons are organosilicon polymers. Means in such polymers there are some silicon carbon bonds that exist. And the monomer of these silicons could be the R2SiO. So these are the repeating units and the monomer of the organosilicons. And this R2 means two R groups are there. So these R groups have carbon group. So there is two CSiC bonds and this O bond, and there is another unit with another from another unit the oxygen will come, and this, such bonds the repetition happens. So what you see, this R2SiO, that this R2 is the one R here, one R here, and one bond, this bond is the Si bond, and you see one O group will come here as well. The same repeating unit is the repetition we call the monomer. So it forms a long chain. So the starting material for the manufacture of silicones are alkyl or aryl substituted silicones. The starting materials, although the monomers are different and the starting materials are different. Monomers, you see the formation, this oxygen is there, but the starting material we start with the silicon chloride. The, and these silicon chlorides have alkyl or aryl substitution. The alkyl that we know R group or aryl we know aryl group, it could be the benzene phenyl group or some other groups as well. So this silicon chloride, you know, the its formula will be SiCl4. But if some chlorides are replaced with some R groups, suppose n R groups are there, so the similarly just to keep the valency of silicon 4, what you have to do is you have to remove 4 n chloride groups as well from this entire structure. So if Rn Si, then this will become Cl4 minus n, so that if you add n plus 4 minus n, it will remain be 4. So because this is because silicon has only 4 covalency, it shows only 4 covalency. Where R is alkyl or aryl group, and alkyl and aryl groups, you know, methyl is an alkyl group, phenyl is an aryl group. So when a methyl chloride reacts with silicon in the presence of copper as a catalyst at temperature 570 Kelvin or more, various types of methyl substituted chlorosilane of formula MeSiCl3, Me2SiCl2, Me3SiCl, and with a small amount of Me4Si are formed. These are all methyl silanes. And so the chlorosilanes, this is chlorosilane, this is dimethyl dichloride silane, or maybe one can say dichlorodimethyl This is trichloromethylsilane. This is chlorotrimethylsilane. And this is tetramethylsilane. So these are silane groups, and these kind of groups will be formed. And once the hydrolysis is done, see the Cl groups are there. On hydrolysis, what happens? The Cl group will be replaced with by the OH group. Now what we see, you see the introduction of OH groups which will be there in the monomer. So on the hydrolysis, these groups with all the chlorosilanes will be replaced. The Cl2 group will be replaced with the two H groups, and when we condense it, and which when followed by the condensation, polymerization happens, and which yields a straight chain polymer. And the straight chains the polymers is because this R2, R group and R group, these two groups, the joining at these two groups are not possible, so the branching is not there. We see only the straight chain polymers. The example, the clear, if you see, this is the methyl chloride. When it reacts with silicon in presence of copper powder above 570 Kelvin temperature, we see there are many chlorosilane that can be formed. One useful chlorosilane is dichlorodimethylsilane, and dichlorodimethylsilane on the hydrolysis it forms dihydroxodimethylsilane. dihydroxodimethylsilane, and this dihydroxodimethylsilane on polymerization, here the four molecules of dihydroxodimethylsilane is shown here to be used. And when this is polymerized, what we see the removal of water molecules from here and see the formation of SiO-Si bond. SiO-Si. So this OH and one H, means water molecule will be removed, that is here, and so we see HO, Si, CH3, CH3O, Si, then CH3, CH3OH, and if this OH forms bonds with this, so you see the formation of linear chain. This OH can also react with another unit of dihydroxodimethylsilane, and we see the formation of silicon, and so this is the structure of silicon one can consider. So this O group is there, so this represents another unit, and this is the one unit that we have shown here. This R2 SiO unit, this is R2, R is methyl here, so methyl, and this is silicon, O, and then this O forms bond with another silicon, CH3, CH3, then another oxygen, and so this we can have n such units of this monomer, and this we call the silicons. The chain length of the polymer can be controlled by adding CH3 thrice SiCl, and so one can control the chain length. So how long the chain will be for the silicons, one can control this using this material Me3SiCl. So one we use this is Me3SiCl is the same CH3 group, methyl group we also represent as Me, and it blocks the end as shown below. So if suppose this n groups, such groups are there, these groups, and usually this OH will be there at the end, such a terminus, and even if the polymers are there, for the understanding purpose, we may use this structure to see what kind of reaction it might follow. So this n groups of this is have be used, and the some polymerization will happen, and polymerized silicon will be formed, and another this group is add. So water after the mm, mm, after the hydrolysis OH, the Cl will be replaced with the OH, and that is there. So this OH and this OH will be formed, and there is no oxygen atom at the terminus of the silicon, and so this will now ends the further polymerization or further addition of another monomer units, so it blocks the ends, and this is kind of the reaction that we see. So this water molecule will be removed in the polymerization, and we see this the silicon formation, and this ending, to end this polymerization we add CH3SiCl just to control the polymerization reaction, or to control the chain length of the polymer we use this material as well. The silicons being surrounded by non-polar alkyl groups, you see the silicons are surrounded by these methyl groups. The Si, this is also CH3, CH3, CH3 oxygen atoms will be buried inside, and it's surrounded mostly by the alkyl or methyl groups, and so it has as the water repellent, it has what hydrophobic tendency, and so the silicons being surrounded by non-polar, these are non-polar groups, alkyl groups are water repelling in nature, so they are hydrophobic in nature. So silicons are hydrophobic in nature, means they are water repelling in nature. They have in general high thermal stability, and they have very high thermal stability. One of the reasons is again silicon oxygen bond formation, high dielectric strength, and they also have high dielectric strength and resistance to oxygen and chemicals. So they also have the resistance to oxygen and some other form of chemicals. Means these Si bonds are stronger, and Si carbon bonds are also a strong bond. So they have resistance to most of the chemicals and oxidation. The silicons are used as sealants. Sealants are the kind of sealing material that is used to form a hard coating on a porous surfaces. So porous surfaces are there, you just use something, a hard coating, so that it doesn't allow something to pass. And so these silicons are used as sealant, and so it won't allow water to pass through. So in the coating, once you do the coating, it will use as a water repellent material. So they are used in sealant, greases, electrical insulators, so they are insulators, and for waterproofing of fabric. So waterproofing of fabrics as well, it is used as a sealant. So it can, you just use a hard coating on the surface of the fabric, and you see it won't allow water to pass through it because it has this hydrophobic groups or the water repelling group. Being biocompatible, and they are also biocompatible, they are also used in surgical and cosmetic plants. Uh, and they are so their user in the surgical and cosmetic plants as well. So let's see what is this question. What this question tells: what are the silicones? Just a question: what are the silicones? And we have seen what are the silicones. The simple silicon consists of Si, this bond, this bond will be carbon, carbon bond, Si, carbon bond, Si, carbon bond, O, n chains in which alkyl or phenyl groups occupy the remaining bonding positions on each silicon. So the remaining bonding position is this position will be occupied by either alkyl group or aryl group. Instead of methyl, one can also have phenyl, or methyl, one can have ethyl, propyl, any such groups which are called alkyl groups. And they are hydrophobic and the water repellent in nature. Let's now study about the silicates. A large number of silicate minerals exist in nature. And the silicate minerals, what we know, they exist in nature, and the examples of the silicates are the basic units of the silicates are SiO4 4 minus. So the SiO single bonds are there, and each oxygen contains one negative charge. So this we call the basic unit of the silicate structure. So some of the examples of the silicates are feldspar, zeolites, mica, and asbestos. So zeolites, mica, feldspar, and asbestos are examples of silicates. The basic structural unit of silicates is SiO4 4 minus. So each oxygen atom has one negative charge. So there is only there is only single silicon oxygen bond, and there is a single bond between silicon and oxygen atom, in which silicon atom is bonded to four oxygen atoms in tetrahedral fashion, and that you see here the silicon atom, it forms single bond with four oxygen atoms in the tetrahedral fashion, and this angle you see the perfectly 109 degree 28 minute and the tetrahedral fashion. The in silicate and the silicate, either the discrete unit is present, this is the discrete unit is present, or a number of such units are joined together via corners by sharing 1, 2, 3, 4 oxygen atoms per silicate unit. So one can have, if one oxygen share another SiO3 group on this SiO4. So between two SiO3 groups, one oxygen will be there. So the another tetrahedral unit will be, because this oxygen will also form bond with the another SiO3. So that will also be another. So one SiO2 tetrahedral unit suppose is associated here, so it will form a linear chain. If the two tetrahedral units may also form here, three, and one can see the four tetrahedral units are also associated to all the four oxygen atoms, and thus we see the three-dimensional structure of the silicate as well. If all the four oxygen atoms are attached to four different tetrahedral units and in the entire crystal, and so with such repetition it forms a three-dimensional structure. And when silicates units are linked together, they form chain. So if one over one, so it will form chain. It may form ring one over another, and it comes here one, another, and comes joint, so it will form ring. It may form seat, so two where these, so it will form a seat or three-dimensional structure as well. The negative charge on silicate structure is neutralized by positively charged metal. So whatever the negative charge is there on the silicate, it will be neutralized by positively charged metal in the cation. If all the four corners are shared, as I said, all the four corners are shared with other tetrahedral units. And what will the tetrahedral unit? If another unit will come, that will be only SiO3 because one oxygen is already there, which will form bond with the silicon. So that will also silicon will have a tetrahedral geometry, so that will be tetrahedral unit. So to add a next group, it will be only SiO3, not SiO4. So if all the four corners are shared with other tetrahedral units, three-dimensional network is formed. And the two important man-made silicates are glass and cement, and the three-dimensional network will be formed. And the examples of the two important man-made silicates are glass, that you know, and the cement. And one can also have the representation of silicates, the monomer unit, and what we see this structure you can show as this as well. You just rotate this structure so that this oxygen in such a way that this oxygen comes exactly below the silicon, and it goes beyond the opposite side of the observer. So I am just rotating this in this fashion and just rotating this in this way. So this oxygen and silicon bonds will go away. So if I am not able to see oxygen, so that representation one can see. This is similar to the new one projection you might have studied in the organic chemistry. So what we see only silicon, and this silicon and three oxygen atoms will be there, like in it will look like a triangle, equilateral triangle, and so this triangle in C, and another oxygen atom will be beyond the observer, and that oxygen atom is shown as the circle. So this circle represents oxygen atom, and this dot represents silicon, and so there is a negative charge, this negative charge on this oxygen atom, and not on the silicon, and three other oxides are there. So oxygens are actually represented as the circles in this representation. Now let's talk about the zeolites. So if you know the silica structure what it was, let's again see the silica structure just in the two minus though it's a three-dimensional structure. In the two dimensional silica, SiO4 bonds, four SiO bonds are there, and one oxygen forms two single bonds with two silicon atoms. Now, if in the silica structure, if you replace one silicon atom from the aluminum, so what you see, there will be some negative charge on this because oxygen is there in the form of oxide, and one of the oxygen, if the four oxygen atoms are there in the silicon here, if you replace silicon with the aluminum, aluminum can have only plus 3 covalent, means oxygen, highest oxidation state could be plus 3, and four oxygens here are for minus charge, so there will be one extra negative charge, and this silicon can have plus 4 as the highest oxidation state. So it actually balances all the negative charges that are there on the oxygen atom. But if you replace some of the silicon with aluminum, there will be some negative charge that appears around the aluminum, and because of the oxygen atom and the charge on the oxygen, and now this extra charge one can actually balance with the cationic groups like 2Na plus. If two aluminum replaces two silicons, so there will be two negative charges, and these two negative charges will be balanced with two Na plus ions. So if aluminum replaces few silicon atoms in three-dimensional network of silicon dioxide, the obtained structure known as aluminosilicates acquire a negative charge. And this aluminum, we call this new structure we call aluminosilicate. Earlier it was a silica or SiO2 or silicon dioxide. This structure we call aluminosilicate. And silicate, if you remember, this is the silicate structure. This is the aluminosilicate, and this aluminosilicate, the cations such as Na plus, K plus or Ca2 plus balance the negative charges. Whatever the negative charges are there, it will be balanced by Na plus, K plus or Ca2 plus ions. If it is Ca2 plus ions, only one Ca2 plus ions requires to balance these two charges, and if it is Na plus or K plus, we require two such cations. These examples of aluminosilicates are feldspars and zeolites. So zeolites and feldspars are examples of aluminosilicates, and the silicates that we study here that we have seen. The examples are feldspar, zeolite, mica, and asbestos. They are all silicates. Zeolites are widely used as a catalyst. Zeolites are what? They are aluminosilicate. They are widely used as a catalyst in petrochemical industries for cracking of hydrocarbons and isomerization. So, for cracking of hydrocarbons or isomerization of hydrocarbons, zeolites are used as a catalyst. The example is the JSM5, which is a type of zeolite is used to convert alcohols directly into gasoline. So JSM5 is a type of zeolite which is used to convert alcohols directly into gasoline, and this shows what will be the pore size of the zeolite. That is not in your syllabus. The hydrated zeolites are used as ion exchangers in softening of the hard water, and this point we have studied in the hydrogen chapter. So the chapter that is there in the soft and hard water, how zeolites help in softening the hard water, that is there. I have described it in much greater detail, so you can refer that chapter as well from here. Now from this is the end of the chapter, so I'll stop this recording and the lecture here, and we will start a new chapter afresh from our next class.